Virtualization fundamentally changes how boundaries, isolation, and shared risk work in modern environments, and that shift has deep security implications. When you move from dedicated physical systems to virtualized infrastructure, you are no longer relying on physical separation alone to contain faults or attacks. Instead, you are relying on logical boundaries enforced by software layers that multiplex shared hardware across many workloads. This creates enormous efficiency and flexibility, but it also means that a weakness in the control layer can have impact far beyond a single system.
Understanding virtualization is therefore about understanding where trust is placed, how isolation is enforced, and how shared components can become shared risk if they are not governed carefully.
Before we continue, a quick note. This audio course is a companion to the CISS books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. At its core, virtualization abstracts physical hardware into virtual machines and managed resources that behave like independent systems. A virtual machine presents its own operating system, storage, memory, and network interfaces, even though those elements are ultimately backed by shared physical components. This abstraction allows workloads to be created, moved, resized, and destroyed far more easily than physical systems ever could. From a security perspective, abstraction is a double-edged sword because it hides complexity while also hiding dependencies. You gain flexibility and speed, but you lose the intuitive clarity of knowing exactly which disk, which network card, or which processor a workload uses. Security design has to compensate by making those hidden layers visible through policy, monitoring, and explicit ownership. The hypervisor is the control layer that makes this abstraction possible, and it mediates access to central processing unit time, memory, storage, and devices for each virtual machine. It enforces isolation by deciding which guest can execute when, which memory pages belong to which guest, and how input and output requests are handled. Because the hypervisor sits below the guest operating systems, it operates with very high privilege, and a compromise at this layer can undermine all guests running above it. That makes the hypervisor a high-value component from an attacker's perspective and a critical trust anchor from a defender's perspective. Strong hardening, limited access, and careful update management are essential because the hypervisor is not just another service, it is the referee for the entire virtual environment. Isolation is the primary security promise of virtualization, and it aims to prevent one guest from impacting another guest or the host itself. Proper isolation means that a fault, crash, or compromise in one virtual machine should not allow access to another virtual machine's memory, storage, or execution context. In practice, isolation depends on a combination of hardware support, hypervisor correctness, and configuration discipline. Side-channel attacks, misconfigurations, and vulnerabilities can weaken isolation, even when the architecture is sound. This is why virtualization security is not just about trusting the design, but about continuously validating that the isolation boundaries are holding under real conditions. Resource pooling is another defining feature of virtualization, and it introduces effects that are unfamiliar in dedicated environments. When many virtual machines share the same physical resources, activity in one guest can influence the performance of others through contention for processing time, memory bandwidth, storage input and output, or network throughput. These noisy neighbor effects are often discussed as performance issues, but they also have security implications. Resource exhaustion can be used as a denial of service technique, either accidentally or intentionally. And it can also create side channels where one workload infers information about another based on timing or availability.
Capacity planning, quotas, and monitoring therefore become part of the security story, not just an operational concern.
Snapshots and images are powerful features in virtual environments because they allow rapid cloning, rollback, and distribution of systems.
A snapshot captures the state of a virtual machine at a point in time, while an image is often used as a reusable template for creating new instances. These copies contain operating systems, configurations, and often sensitive data or credentials, which means they must be protected with the same rigor as running systems.
An unsecured image can be a blueprint for compromise if it includes outdated software or embedded secrets.
Governance must ensure that snapshots and images are inventoried, access controlled, scanned, and retired when no longer needed, because forgotten copies are a common source of exposure. Virtual networking adds another layer of abstraction by implementing switches, routing, and security controls in software rather than in dedicated hardware. Virtual switches connect virtual machines to each other and to external networks, and they enforce rules about which traffic is allowed to flow. This creates flexibility, but it also means that network security depends heavily on correct configuration of software-defined components. Errors in virtual network rules can expose services unintentionally or collapse segmentation that teams assume is in place. Because virtual networking can be created and modified rapidly, change control and visibility are essential to prevent accidental flattening of network boundaries.
The management plane is the interface through which virtualization infrastructure is controlled, and it represents one of the most sensitive attack surfaces in the environment.
Through the management plane, administrators can create and delete virtual machines, attach storage, modify networks, take snapshots, and change security settings. Compromise of this plane effectively grants control over the entire environment, regardless of how well individual guests are hardened. Strong privileged access limits, multi-factor authentication, separation of duties, and detailed logging are essential to protect the management plane. It should be treated as a crown jewel system because its power far exceeds that of any single virtual machine. Cloud infrastructure extends virtualization by adding provider-operated layers and a shared responsibility model. In cloud environments, the provider manages the physical facilities, hardware, and core virtualization platform, while the customer manages the configuration of virtual resources, identities, and data. This arrangement can improve security by concentrating expertise and standardizing controls, but it also introduces dependency on the provider's design and operational practices. Customers must understand which controls they can influence directly and which are provided as part of the service. Security failures often occur when responsibilities are assumed rather than explicitly defined, leading to gaps at the boundary between provider and customer duties.
Multi-tenancy is inherent in cloud infrastructure, which means many customers share the same underlying platform even though their workloads are logically isolated. This increases the importance of configuration correctness, identity management, and monitoring because isolation is enforced primarily through software. A misconfiguration that exposes a resource publicly can have immediate and global impact because cloud services are internet accessible by design. Monitoring becomes critical to detect misconfigurations, unusual access patterns, and unexpected resource creation. In multi-tenant environments, you assume that other tenants may be hostile, so your controls must be resilient even when sharing physical infrastructure with unknown parties. Ephemeral resources are another characteristic of virtualized and cloud environments, and they change how logging and asset tracking must be approached. Virtual machines, containers, and supporting resources can be created and destroyed automatically in response to demand, sometimes lasting only minutes. Traditional approaches that assume long-lived servers with static names and addresses are not sufficient. Logging must be centralized and near real-time so that evidence is captured before the resource disappears. Asset tracking must rely on identifiers, tags, and automation rather than on manual inventories because the environment is in constant motion.
Orchestration systems automate the creation, scaling, and configuration of resources, which increases speed but also increases the potential impact of mistakes.
When orchestration logic is flawed, it can rapidly propagate misconfigurations across many resources. Guardrails, such as policy enforcement, template validation, and approval workflows, become essential to prevent unsafe changes from being deployed at scale. Orchestration also concentrates authority because the system executing the automation often has broad permissions.
Securing orchestration systems therefore requires careful privilege management, monitoring, and testing because they are powerful amplifiers of both good and bad decisions.
Shared storage and object services are common in virtualized and cloud environments, and they require careful permission modeling. Storage services often support fine-grained access controls, but misapplied permissions can expose large volumes of data. Because storage is decoupled from individual compute instances, access decisions are driven primarily by identity rather than by network location. This makes identity and access management central to storage security, and it increases the importance of auditing who can read, write, and share data. Replication and backup features also create additional copies that must be governed consistently to avoid unintended exposure.
Virtualization and cloud infrastructure reshape isolation and control ownership by replacing physical boundaries with logical ones and by distributing responsibility across multiple parties. Isolation is enforced by software layers that must be configured, monitored, and trusted, while shared resources introduce new forms of contention and shared risk.
Management planes and orchestration systems become critical control points because they can influence large portions of the environment at once.
Cloud models add efficiency and scalability, but they demand clarity about responsibility and discipline in configuration and identity management.
When these environments are understood as layered systems of trust and control rather than as opaque platforms, security decisions become more deliberate and more resilient.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.